So part of the goal of this class is to dig down into how does our microcontroller work, how does the code work, and eliminate anything that feels like magic. So if you've ever done programming before where there was a run button or a compile button where you write your code, you hit compile, and then out pops an executable, it feels a little bit like magic. And if you're using a system like an Arduino, it might feel like you don't quite understand why the code works, especially when you go from one type of Arduino to another type of Arduino. There are just steps in there that don't make sense. So let's dig down into the compilation process of the C program, not to the level of what exactly, what are the voltages passing around inside of the CPU, but down to a level that makes a little bit more sense, and that we can try to figure out exactly how big does our code end up being, how much memory does it take inside of the program space of our computer or microcontroller, and how long does it take to run? How fast does it run? Like when I say I equals 1, does that take one clock cycle or does it take many clock cycles? So our first attempt at understanding this is going to be to dig down into the compilation process and see that it's not magic. It's just a bunch of steps, and each step is another process. Unfortunately, one of those processes is called compiling, but it doesn't represent everything. So when we talk about the compilation process or compile your code, we're actually meaning do a lot of steps, and one of the steps inside of there is compile. So what is the first thing that happens? We've got our C source code. So the code that you've written has an int main inside of it and a return 0 at the end. Maybe you have an H file, maybe you have several C files. So that's our initial source, and the file types are C, like .c, maybe .h, maybe some other things. So when we run, say, GCC, or we hit the compile button inside of our IDE, the first thing that happens is we go through the preprocessor step. So the preprocessor is actually a program. It opens up our C file, it edits the C file, and then it saves it as a .c file. Now this is an intermediate step, so when everything is all said and done, it disappears, so we don't get to see what the difference was. And we're going to investigate this further in the future, but inside of your C code, you've probably noticed that we have some pound include statements, we have some pound define statements, we can have a pound if, pound end if. There's a whole language for the preprocessor that starts with pounds and does things like find another piece of C or H code and copy it in, or replace anything that starts with pound define with an actual number. So it's kind of like an advanced copy-paste function. The output of this is going to be kind of a longer file because we're taking other files and squishing them into our original C code. That is going to go to the actual compiler, which is another program like the preprocessor, and its output is going to be a .s, which stands for assembly code. So the compiler is a program that knows exactly what are the functions that our CPU can do, and it will turn the C code into the assembly lines of code that the processor understands. So we call these like specific machine instructions. But it's still human readable. We can open the .s file and we can see what the assembly commands mean. And if we went and read the manual for our CPU, we could actually figure out what those things do. And many microcontroller programmers still, they don't even know C. They'll just write their code directly in assembly. The problem with doing that is that the code becomes very long. A few lines of C might turn into a couple or dozens or hundreds of lines of assembly code. So we're saving time by writing our code in C instead of writing it in assembly. But at the disadvantage of maybe we don't understand what some lines of C get turned into assembly. So at some point we'll do some homeworks where we actually count the lines of assembly that are made from the compiler from our code, and we'll be able to figure out exactly how long does a specific function take by counting the lines of assembly. So where does the assembly go? The assembly goes to the assembler, another program that outputs a .o or object code. And this is going to be actual machine code. And it will be in binary. It will no longer be human readable. So if you open a .o file in a text editor, you won't be able to read it. You know, the data will be not in ASCII characters. So we'll talk about ASCII as well at some point. So that's no longer something that we can interpret. But it's not the final executable. A .o file is still relocatable. So all of the functions in memory have addresses, and the addresses are relative to each other, but they haven't been given the final address that they'll go inside of the computer or the microcontroller. So the .o code goes to the linker program, and the linker outputs an executable. So the linker assigns all of the O functions final addresses in memory where they will live, produces your executable file, which is not human readable. And then sometimes this will go further, especially for a microcontroller, and it will get turned into a hex file. So this is not hex like hexadecimal numbers. This is turning your executable object code into ASCII code that we can read again, and that's what we can then send to the microcontroller to have it program itself. So this is what we would consider kind of a magic step. We have our original C code. We hit the compile or we run GCC. It goes through several steps. Each step has a different type of output file until we eventually get to our either executable or hex file. Then it goes back and it cleans up and it deletes all these other ones so we can't see them. But it's possible that we can run the compiler, the compilation process, so that it doesn't delete these and we can see them, or we can go backwards and we can investigate why did the compiler choose to do certain things. And the compiler has options so that we can say, actually, I'd like the code to run faster. Can you optimize to run fast? Or I need the code to be smaller so it fits in less memory. Can we maybe sacrifice some speed so that the code fits in a smaller space? So we'll come back to this several times throughout the class to discuss what exactly, specifically for our microcontroller, is happening when we run the compiler.